Alright, welcome back everybody. In this video we're going to look at the direct comparison test and how we can use it to show convergence or divergence of series. And we're also going to look at absolute convergence and how we can use that along with the direct comparison test to show convergence or divergence of series. Alright, so first the direct comparison test. If we have a series with no non-negative terms, that series converges if there's another convergent series that we know where all the terms in the series that we're looking at are smaller than all the terms of the convergent series, smaller than or equal to, for all n greater than some integer n. And similarly, it diverges if there's a divergent series where the series we're looking at is always bigger than or equal to the terms of the divergent series that we know. This, calls back to when we looked at direct comparison and limit comparison tests for integrals that we looked at quite some time ago. Also operates under the same fundamental principle. If you can find a bigger series than the one you're looking at and the bigger series converges, then the series you're interested in converges. If you find a smaller series than the one you're looking at and the smaller series diverges, then the series that you're interested in will also diverge. A lot of the times here we're going to do comparisons to p-series. We know that these p-series converge when p is greater than 1 and diverge when p is less than or equal to 1, and so they make for a nice, quick, easy comparison for us in many cases. Alright, so let's go ahead and look at these examples, determine if these converge or diverge using the direct comparison test. And so we want to compare the sum from 1 to infinity of 5 over the quantity 2 plus 3n plus n to the fourth to some other series that we know converges or diverges. And the series I'm going to compare this to in this case is the sum from 1 to infinity of 5 over n to the fourth. Now we know that 5 over n to the fourth converges because 1 over n to the fourth converges because it's a p-series with p greater than 1. So now all I would need to do, since we know that this series converges, is we need to show or argue that 5 over 2 plus 3n plus n to the fourth is less than or equal to 5 over n to the fourth. And if you reason your way through that, for any value of n, the denominator of this first fraction is going to be bigger than the denominator of the second fraction, and therefore the fraction itself is going to be smaller. So since that function is less than 5 over n to the fourth, and sum from 1 to infinity of 5 over n to the fourth, come on, stylus, and that series converges because it's a p-series with p greater than 1, by direct comparison, the sum from 1 to infinity of 5 over 2 plus 3n plus n to the fourth converges. Alright, on to part B. We're going to compare this to 1 over n. Okay, and we know 1 over n diverges. Now we need to think about the relationship between this and this. The first fraction here has a smaller denominator, hence it's always going to be bigger. So since that's always bigger than 1 over n, and the sum from 1 to infinity diverges because it's a p-series with p greater than 1, with p less than or equal to 1, by the direct comparison test, the sum from 1 to infinity of 1 over square root of n squared minus 1 diverges. Now, what would have happened if I compared it to 1 over n and found that it was less than or equal to 1 over n instead of greater than or equal to 1 over n? Well, since 1 over n is a divergent series, if we found that it was less than or equal to 1 over n, there wouldn't have been any conclusion that we could have drawn. We always need to find a divergent series that is smaller than the series we're looking at, or a convergent series that is bigger. Okay? And in part C, we're going to compare this to 1 over 3 to the n, which finally is not a p-series that we're comparing to. But it is a geometric series, which is another opportunity for us to draw the kind of conclusion that we want about its convergence or divergence. All right, and the series that we're interested in is always smaller than this because it has a bigger denominator, and the sum from 1 to infinity of 1 over 3 to the n converges because it's a geometric series with absolute value of r less than 1. Then by the direct comparison test, we know that the sum from 1 to infinity of 1 over 3 to the n plus 2 converges. And that's how we use direct comparison. All right, continuing on. What was nice with all of those was we had series where the terms were always positive, or non-negative rather. But when we have series that have negative terms in them, we can't really use direct comparison. But we can use the concept that if an absolute, this is the idea of absolute convergence, if a series of absolute values converges, that tells you that the series without the absolute value does what we call converging absolutely. And furthermore, if the sum of the absolute value of a series converges, that means that the series itself converges. So if we have a series with negative terms, in order to show that it converges, we can show that its absolute value converges. Of course, there's limitations to this. If we show that the absolute value of a series with negative terms diverges, that doesn't necessarily mean that the series diverges. But we'll get to that much more later on in the future. All right. Example 5. Show that the given series converges for all values of x. And I'd like to. Now, these series have positive and negative terms when we have negative 1 to the n over x squared. So instead, I'm going to consider the absolute value of this series. And the absolute value of this series is just the sum from 1 to n, or for n from 1 to infinity, of 1 over x squared. Now, are there values of x for which this series converges? Well, no, there aren't. So, if it did converge, we would be able to show that the original series converged, but this series diverges. Imagine, say, x is 2. You know, we've got 1 over 2 squared, and that's the sum from 1 to infinity of 1/4. That diverges by the nth term test. So this diverges, but we can't show divergence, which means this is inconclusive. The only way that this matters is if we can in fact show that the absolute value of the series converges. Alright, let's look at B. I'm going to compare this to, now because sine goes between -1 and 1, the quantity sine of x to the n over n factorial is always less than or equal to 1 over n factorial. And so if I consider the series man, this stylus is really slopping up my writing. If I consider the series sum from 1 to infinity of 1 over n squared, or pardon me, 1 over n factorial, this is going to be smaller than, for instance, the sum from 1 to infinity of 1 over n squared. Once we reach a certain value of n, which converges. And I just compared it to you know, 1 over 2 factorial is 1/2, so it's not smaller yet than. 1 over 3 factorial is 1/6, so it's not smaller than. 1 over 4 factorial is 1 over 24. And so for n greater than 4, 1 over n factorial is always smaller than 1 over n squared, which shows that it converges. And therefore, the conclusion that we can draw is that this series, the original series that we were talking about, converges for all values of x. Alright, that's the end of this video. See you guys next time. Have a great rest of your day.